temperature for 8 selected years. So this is a two-dimensional graph. The horizontal scale represents the time. As you can see, it starts from 1950 and then 1960, 1970, all the way to 2015. So the horizontal x-axis is the time in year. And the vertical scale, if you turn your head, it says degree Fahrenheit, is the average temperature for the year. As you can see, in 1950, the average temperature is 56.94, and 2015 has risen to 58.09. I wonder what's now after 9 years. I believe the trend is just keep going up. So we have three parts here. The part A is to estimate the yearly increase in the average global temperature rounded to the nearest hundredths of the degree. So part A, I wanted to make it clear. Part A actually is to find the slope. Okay, why is the slope? We might remember slope is a rise over run. Rise is the vertical change, is the temperature change in the temp. And run horizontal change in year. Since we are looking for the yearly increase in temperature, so we are actually looking for the slope of this trend. We are actually doing a linear model here. Linear model. As you can see, the trend is approximately a linear increasing trend. And the first part A, is to find the slope. Yearly means every year, right? Every year, on average, what's the change in temperature? So let me tell you exactly what do we do for part A. It's pretty simple. Just look at this number and this number, okay? Part A, use the biggest number, the highest temperature in 2015, 58.09, to minus the lowest temperature in 1950, which is 56.94, and use the difference to divide by the change in year. So 58.09, that temperature corresponding to year 2015. Use 2015 to minus the corresponding year for the lowest temperature, 56.94 Fahrenheit, which is 1950. Okay, and so part A, when you see something like this in Pearson, in MATLAB, just do this. Use the biggest temperature to minus the smallest temperature. That's the numerator. Denominator, use the corresponding year for the highest temperature to minus the corresponding year for the lowest temperature. And let's do the math. Do you guys have a calculator? I'm gonna use my handheld calculator, and you can do the same. So numerator 58.09 minus 56.94. The numerator gives me 1.15. The denominator 2015 minus 1950. That gives me 65 years. And then I'm using the numerator 1.15 to divide by 65. I got a decimal very long. Is around equal to 0.17. 0.017. 0.01769. 23077. But you do not enter that decimal to the cell. Read the question very carefully. We need to let's go back to the question. the rounding instruction. Round to the nearest hundredth as needed. Whatever inside the parentheses, when you work on the Pearson for this course, whatever inside the parentheses, those are important information. Please make sure you do not ignore whatever inside the parentheses, okay? And this tells us how do you round the result and then put it in the cell, okay? Round to the nearest hundredth. Where is the nearest hundredth? This is tenth, this is hundredth. So nearest hundredth means we are going to keep 2 decimal places to the right of the decimal point. And we look at the digit right behind the rounding place. The rounding place is 1, right? The digit behind is 7. Because 7 is bigger than or equal to 5, we are going to round it up. So this number, when we keep 2 decimal places, the number is going to be 0.02. Okay, so here we are going to enter 0.02 Fahrenheit per year. 0.02. Right? And that's part A. Again, part A is actually to find the slope of the straight line that could model the linear trend in a graph. Part B, let's read the part B. Write a mathematical, I have the part B here. Write a mathematical model that estimates the average global temperature T in degrees Fahrenheit X years after 1950. So part B, we are going to use 2 variables, T and X. We're going to be very clear about what does T represent and what does X represent. T represents the temperature in Fahrenheit. X represents the number of years after 1950. That means when the year is 1950, X equals 0. Okay? X here represents the number of years after 1950. So when the year is 1950, that's the initial year. X is 0. When the year is 1960, X is 10. Do you agree? When the year is 2015, X equals 65, and so on. You see the relation between the year and the X. So we need to set up an equation. The equation can describe the linear trend. It has to be linear, okay? We only learn linear in this course. So are you guys familiar with the slope-intercept form of linear equation? Y equals mx plus b. Does this equation ring a bell? Y equals mx plus b. This is the slope-intercept form of a straight line. Linear equation in 2 variables, straight line. So this is a straight line, okay? Yeah. So we are going to set up a linear equation in a slope-intercept form to model the situation. And the slope, actually, we already found. Slope is 0.02. Okay? Slope is 0.02. And the B here is the initial temperature, initial T. In other words, B here is the temperature, the value of T when in the initial year in 1950. So it's gonna be 56.94. All right. Once you understand, if you remember straight line pretty well, and will be a very doable problem. It's been a while, but so it's a straight line. So we are going to enter this equation, all right? We're gonna enter this equation for part B. Again, m here is the slope. We found the slope from part A, 0.02. So m is 0.02. B remember it's a y-intercept. Y-intercept is the y value when x equals 0. So when x equals 0, that's year 1950. In year 1950, the temperature is 56.94. So the initial temperature is 56.94. Let's enter that here. A mathematical model that estimates. So as you can see, it's not exactly linear straight line. So this is just the estimation. In degree Fahrenheit, x equals after 1950 is. Be aware you already have T equals outside the box. So you do not, listen, you do not enter this any again, okay? You do not enter that again. You already have T equals, the y value equals, the function equals. So we're gonna enter 0.02 x plus the initial temperature 56.94. 56.94. See that? So part B is just to figure out the linear equation, the equation of the straight line that can model the linear trend from the picture. Part C, the model, I have a part C here. If the trend shown by the data continues, use your model or linear model from part B to predict the average global temperature in 2040. Okay, so let's see part C. As the problem instructs, for part C, we need to use the result from part B. The part B, we have T equals 0.02x plus 56.94. One of the important significance of a linear model or any mathematical model is to predict the future value of the function. So we are going to predict which year, 2040. The year is 2040. Yeah, we can come here. Remember, we have those when the year is 1950, x equals 0. When the year is 1960, x is 10. When the year is 2015, 15, x is 65. Anybody can help me to figure out when the year is 2040, what's the value of x? Let me repeat my question. Earlier, we analyzed when the year is 1950, x is 0. That's the initial year. We see that as the very beginning. When the year is 1960, then x equals 10, right? Because that's 10 years after 1950. When the year is 2015, x value is 65. That's 65 years after 1950. My question was, what's the value of x when the year is 2040? 2040. 90. Awesome. Thank you, Mary Ann. That's correct. 90. Yeah, that's 90 years after, oops. That's 90 years after 1950. 1950. So all we need to do, since the part C is to predict the temperature, to predict the value of T, all we need to do is to plug in x equals 90. Okay, let's plug in. T equals 0.02 times 90 and then plus 56.94. I'm going to use my calculator. You can do the same thing. In this case, I'm not going to show you. I don't have a camera to show my calculator. I'll just verbal here. 0.02 times 90 gives us 1.8. 1.8 plus 56.94 gives us 58.74. That's the temperature, the predicted temperature in 2040, no, 2024, I'm sorry. This year is 2024, but it's 2040 in the future. So we're going to enter 58.74. Let's see, again, whenever you see something in the parentheses, please do not ignore. Round to the nearest hundreds. That means you're going to keep 2 decimal places. Use the answer from part B to find the answer. Yeah, we did. We used the equation that we had. What's my value? 58.74. 58.74. Hold on. Did I... What? Isn't here 2040? Oh, I understand. Because that was the question I copy paste earlier before the class, we start the class, and then I logged out, and then now I log in again, so the question changed. The question structure stays, but the numbers changed. Part C here is to predict the temperature for 2025. My bad. So let's do it again, okay? This time we are going to plug in the year 2025. Then help me out. When the year is 2025, what's the value of x? What's the value of x? Do you agree? Yeah, do you agree? 75, right? Let's see. Perfect. Yeah, correct. So now we are going to plug in x equals 75 instead. Yeah, we're going to change this to 2025. I copy pasted this question earlier, but I logged out. When I log in again, the question, the system giving me a different number. That's why we entered the wrong number. So we do 2025. For the year 2025, x equals 75. So we're going to plug in x equals 75. We multiply 75 by 0.02. We have 1.5. And we add 1.5 to 56.94. We got a 58.44. Do you have the same thing? There we go. You see that, guys? In previous semesters, this question is the challenging question for this section. I hope the explanation for the 3 steps could help you. And this is actually a very good problem about the linear modeling. So the trend is a linear increasing pattern. The first part, when we try to find a yearly increase, estimated yearly increase for the temperature, that's actually to find the slope of the straight line that could estimate the linear trend. And use the biggest temperature to minus the smallest temperature as the numerator, and you use the corresponding year for the highest temperature to minus the corresponding year for the lowest temperature. Use the denominator, put in the denominator, and then you'll find the slope. Make sure you round it properly. And the part B is to find the slope-intercept form of the straight line. Part A already gave you the slope. All you need to do is to find the initial year. So the initial year here is 1950. Just to put a number here. And then part C is to use the model to predict the temperature in the future years. Important thing is to figure out for a certain year the value of x, and then you plug in value of x to find the predicted value for the temperature in the future years. And let me know, is that